That's.
Yep, got it. Thanks. Yep, it's all yours.
So you share my see my screen, right?
Yes, we can see that.
Good.
Very
Thank you.
fantastic.
Until now, it is fine. Thank you, Chairman, for introducing me. I am from Harbin Institute of Technology in China. I am originally hailing from Bangladesh. Previously worked in Ruet, Rajshahi University of Engineering and Technology. I have been working in China for more than 10 years. Before that, I worked in Pretoria University in South Africa. I worked as a postdoctoral fellow in Hong Kong and got a master's and PhD from Japan Kitami Institute of Technology. My talk will be energy harvesting from flow-induced vibration of black bodies. We know our physical structure itself is a blob and like a cylinder, essentially. You see from the left top corner, a cylinder is oscillating due to flow. And there is one small cylinder in front of it. And in the right top corner, you see the baby is exercising. How it's getting itself the vibrations. You'll find one toothbrush in his right hand. That toothbrush actually helping him to get the excitations. That we call the added mass effect. Okay. And in the third video, you'll see that one foil is oscillating due to flow. So if the flow is, if the foil is oscillating, that means we can harness some energy from the oscillation. Here is the presentation outline. I will give you an overview of wake and flow-induced vibration. Both wake and flow-induced vibration are interconnected. Then I will show the catastrophic consequence of flow-induced vibrations. Then blessing consequence of flow-induced vibrations. Then 4, 5, 6, I will give you the flow-induced vibration of a cylinder in wake, energy harvesting from cylinder, and energy harvesting from inverted foil. Then finally, I will make some conclusions. Let's discuss about the wake. We know about the Karman vortex state or Karman wake that generates from any kind of blob body, something like this. And you can see here the very nice picture. That's Karman states itself. It has a how do I say, that's charming because of uniform distribution of vortices. It's not only for the cylinder in wake. If you have large scale structure like an island on the ocean, then you will find the Karman vortex in the cloud and also in the ocean. Where you will find the blob body and flow, you will find the Karman vortex setting. This Karman vortex setting has a quite catastrophic consequence in our daily life. Like we know the vortex induced vibration, we call it VIV. You'll see here one tower is oscillating due to wind. And we always see this, like when we get on a plane, we always hear the announcement like we are facing turbulence, so please keep your seat upright and fasten your seat belt, something like this. And here there's the huge structure oscillating due to wind. The wind speed was only 17 meters per second. But that causes violent vibration of that bridge. It's oscillating at large amplitude. And finally, it gets collapse. That means, you see, we need a lot of energy to break this suspension bridge. That means wind has energy, huge energy, and also a structure subjected to flow can extract the extract or capture the energy from the wind. If it can extract or capture, that means we can exploit, we can harness that energy and utilize in our daily purpose. And also rain wind induced vibrations. When there's a rain and wind, we have also violent vibrations, like you see, due to rain, we have a rivulet like this, like water flow channel like this on the cable. Here you will see the picture, clear picture. When there's a rain and wind, you will find a violent vibration of a cable of a bridge like this. The cause of this vibration is mainly due the rivulet water channel forms on the cable. Then you'll see here, single structure and two structured vibrations are totally different. You will see here, the single one are not oscillating, but when we have two, when we have two cables, they are interacting each other and have violent vibrations. Then up to now we have seen that actually the flow induced vibration is very destructive, that can cause a failure of even large scale structure. Then we can also use that to harness energy, like if you see from the left top corner, the bladeless turbine, like if you have simply a pole, then it is oscillating, you can get energy from the oscillating structure. If you have the single one, then we call it is like a VIV, circular cylinder, then it is a VIV, vortex induced vibrations. You see, this vibration is mainly from the vortex induced, the vortex heading causing the oscillation of this cylinder. And if you use a long cable, something like with strain gauges, it's oscillated to wave, then again, you can extract energy. We call the flow induced vibration mainly two types. One is the VIV and another is galloping. Okay, you will see here. All these are here VIV, like vortex induced vibrations. We have different regimes, like initial excitation, upper branch, lower branch. All three branches are VIV. Here the amplitude like up to 1 diameter, but here you will see here the VE, the vortex excitation or VIV. This one, the right one, is amplitude is increasing. We call it galloping. Okay. This is the limited amplitude. Like if you increase the speed, then the amplitude will decrease. But for the galloping, it will not stop if you increase the speed. Until the failure, amplitude will be increasing. For square cylinder, if you see at the left bottom corner, itself a single cylinder can undergo the galloping. Up to now, we know a single circular cylinder does not experience galloping. But if we put 2 or 3 or more, then one of them can have high amplitude galloping vibrations. That's due to the interaction between the two cylinders. If you see here, single cylinder wake, here the two cylinder wake is strong, okay, enhanced, but here the two cylinder wake is quite tranquil, weakened wake or Karman vortex heading. Definitely for these two cases, the vortex induced vibration or galloping would be different. You can see here on cases, the downstream cylinder, the flows from left to right in the wind tunnel, the downstream cylinder is vibrating. When I take out the front cylinder, the smaller side, you see the vibration stops, right? When I'm inserting the cylinder again, you see easily the vibration starts. That means the interaction, fluid structure interaction in one cylinder and two cylinder is totally different. Okay, two cylinder may excite galloping or may alleviate the galloping. Similarly, you're like you all were previously bachelors, had a experience in single life. If you compare that your single life and couple life, they're totally different, right? And this difference will depend how you two are interacting each other. Okay. Here, my goal is to investigate what is the effect of upstream cylinder diameter on FIV of the downstream cylinder. This one is oscillating. What is the physics behind it? Okay, for the two cylinder galloping generation, because single cylinder does not experience galloping. Then how can we harness energy from these galloping vibrations? We did experiment in wind tunnel. The wind tunnel has a size like this, cross-section size, height 1 meter, width 0.8 meter, and length 3.0 meter. Turbulence intensity was less than 0.5%. Here is the experimental setup. You will see here the upstream cylinder and downstream cylinder. Upstream cylinder is fixed and the downstream cylinder is spring mounted, okay, hanging on a spring so that it is flexible, it can oscillate. We put two hot wires, one in the gap and another in the wake, and we measure the displacement using laser vibrometer, okay, putting at the top. And here our spring arrangement on the cylinder, we use leaf spring to restrict the motion in the cross flow direction. Okay, to restrict the motion in the cross flow direction. Then what are the variables? Here we change the upstream cylinder diameter from 0.2 to 1D. 1D means identical diameter, both are have the same size. Note that the upstream cylinder diameter is small d and the downstream cylinder diameter is the capital D. That means for all the cases, we have the smaller upstream cylinder diameter or the same size corresponding to 1. We change the flow speed from 1.8 to 32 meters per second. The corresponding, we call the non-dimensional velocity or reduced velocity is 3.8 to 68. And the Reynolds number was here up to the order of 10 to the power 3 and 10 to the power 4. We did PIV measurements to capture the flow structure in the gap and also in the wake. We did the phase average PIV images, PIV flow field at different displacement. That's very common. We're not going through this. Then let's come to the results. If you do flow-induced vibration, you first need to measure the general characteristics of your system, like what is the natural frequency of the system, what is the damping ratio of the system, what is the mass ratio of the system, and mass damping ratio. If you want to get the natural frequency and damping ratio, if you make the cylinder oscillate freely without air, without flow, then you will find a decay of amplitude, something like this. From this decay of amplitude, you can easily find the damping ratio, okay, from the decay of amplitude. And if you get the power spectrum, then you can find the natural frequency of your cylinder system. So here we got the natural frequency 11.72 and damping ratio is 0.0021. Mass ratio was 275. Actually, this is a high because we did experiment in the wind tunnel. If you do the experiment water tunnel, it will be like something 2 or 3, 4 something. Then we see here some results for L over D1. L means the spacing between the cylinder, okay, from the center of the upstream cylinder to the front stagnation point of the downstream cylinder. So the spacing is this 1.0, and we varied the diameter ratio, okay, from 0.2 to 1. That means very small to identical diameter. What you see here, for D over D1, there is no vibration, okay, up to here. The small amplitude vibration we call the vortex excitation, okay. But here we see the large amplitude vibration, we call it galloping. Okay, it is always increasing with UR. UR means reduced velocity. You can simply say it is the flow velocity, like meter per second. Here we found the large amplitude galloping vibration for d over d 0.2 to 0.8. Okay, you can see the oscillation here. Note that this is for L over D1. If we change L over D, the spacing, what happened? We can see here. This is for L over D1, then 1.5 to 2.5, 3, 3.5 up to 5.5. What's interesting here, at L over D 1.5, you see there are only 3 lines. L over D2, L over D equal to also the same until 2.5. So 2.5, we have the 3 lines. 3 lines, this is the corresponding to smaller d over d, means 0.2, 0.4, and 6. We have the large amplitude vibration for these cases. But we don't have for 1.0 and 0.8. If you increase the spacing, then we have only 2 curves. Okay, for 3, 3.5, and 4.0. These 2 curves correspond to only the smallest 2 diameter. Okay, 0.2 and 0.5. And at L over D 5.5, we have only 1. That means the smallest. That means the smaller diameter can generate high amplitude violent vibration for larger range of L over D. So this is we call the vortex excitation. This is we call the galloping vibration, violent vibration, and a smaller d by d or L over d is prone to generate galloping vibrations. Here is the vibration map, okay, in the domain of L over d and d over d. What we see here in this domain, we have the large amplitude galloping vibration. Forget about this because we may not be the expert in this, so forget about this. Our main focus is like a high amplitude vibration occurring in this region. Then how the flow structure modifies during the cylinder vibration, because the flow structure is responsible for the galloping vibration, even for the vortex induced vibration. You see here the flow structure in the gap and wave. How the flow induced vibration is generating is mainly due to the gap flow. You see the gap flow is switching from one side to the other. This gap flow is mainly responsible for the galloping vibration. Okay, and this gap flow, we analyze the results and we found that this gap flow actually gives the energy to the cylinder to vibrate. Okay, this gap flow vortices or the shear layer, and the vortices from the downstream cylinder in a cycle during the oscillation take away some energy from the cylinder. So the energy input comes from the gap shear layers, and energy output from some of the vortices from the downstream cylinder. If we see the instantaneous work done or displacement and CL, we can find that the positive work done when the cylinder moves from the symmetric position to a certain level. Okay, where you see the cylinder moving upward, we have positive CL, highly negative pressure on the upper side. Then when the cylinder reaches near the top, the pressure distribution flips down. Okay, now highly negative pressure on the lower side. That makes the negative work done when the cylinder approaches its extreme. From the top to the symmetric positions all the way, the cylinder gets energy from the flow. That means positive work done. So we understood from here that the cylinder can extract energy from the flow. Then we use a system to extract energy using magnetic damper. You see the system. Damping means that can dissipate energy. Okay, that we can use energy afterwards. So again, the same cylinder system, we use here as a representative d over d 0.4 and for L over d 1 to 4, almost the same U infinity regimes, okay, and the corresponding Reynolds number is here. Here is our setup, okay. We use magnetic damper to extract energy. That means we will investigate the damping effect or energy extraction effect on the amplitude. This is the setup here. Then now we see here the almost same figures. Vertical axis is the amplitude, horizontal axis is the flow speed or reduced velocity at different spacings. Here the different legends is the different damping ratio. Okay, you can say it is a different magnitude of energy extraction. This is the damping ratio. Okay, what you will see here for smallest damping ratio, we have the both VIV and galloping connected. Okay, combination of VIV and galloping. When the damping is large, we have separated VIV and galloping. At large amplitude, galloping is postponed. Onset of galloping is postponed. Similar observation is made for other L over D, like here and here. You'll see when we are increasing the damping or increase the L over D, we see smaller amplitude. Okay.
Professor Mahbub, we have got 5 minutes to conclude. Thanks.
Oh, maybe I was sometimes before the start. Anyway, I'll try my best. Here is the contour plot. What we see, the amplitude galloping vibration at high reduced velocity and smaller damping. Here is the power output. People mainly know about the VIV power output, but you see the galloping power output is very large, even sometimes more than 3 times than in the VIV. Okay, all VIV has large amplitude vibration and large power output. This is the same thing of contour plot. Then energy harvesting from inverted foil. So this is a numerical simulation indeed. We use inverted foil and let them free oscillate due to flow. Then when we are increasing the reduced velocity, we found that theta 0 is the amplitude, angular amplitude of the foil. When UR is about 33 or 34, beyond that, we have constant amplitude vibration is almost 90 degree, beyond the 90 degree, 0.5 that goes up to the 90 degree. And this is the no damping, no power output, the total power output or hysteresis is 0. Okay, you'll see here. This is the instantaneous oscillation and also the moment, corresponding moment. You'll see here, it is happening, the oscillation. You can see if we increase the damping ratio, then how this hysteresis changes. Hysteresis means like the power output. Okay, at a small damping ratio, you will find the both positive and negative hysteresis when you are increasing the damping. Up to here, it's the regime of hysteresis is increasing. Okay, the inner regime area. Then we have actually almost no negative hysteresis. Then again, after that, the regime is inner regime is hysteresis regime is declining. So if we see the power output or the efficiency, we found that the efficiency is maximum at damping ratio 0.13. After that, increasing. That means you need to set the power output corresponding to this damping ratio, then you will get maximum power and maximum efficiency. Then during the oscillation, how this energy comes from, you see, when this goes from mid position to the extreme position, we have the positive output. When it comes from the extreme to the middle, then we have negative power output. That means flow gets energy from the foil. This is the opposite scenario in the lower side, so you'll understand. Then come to the conclusions. We found instability of the shear layer between the 2 cylinders. That actually the reason behind the generation of galloping. We have the instability because A smaller cylinder shear layer can go up or down. They have the choice to go up or down. That means it has the instability. And power in VIV regime almost more than 3 times larger than the VIV regimes. People mainly consider VIV, but galloping gives larger amplitude and larger power output. And when we are increasing the UR, we found large amplitude vibration oscillation of the foil when UR is greater than 33. Okay, and in this regime, high amplitude regimes, we have the highest efficiency when damping ratio is 0.13. So we found the highest efficiency at 0.13, and particularly the vortices, when it's coming back, is stronger. That actually extract energy from the foil. When the foil moving from the mean to the extreme, you see the vortex is weaker. That means foil getting energy from the flow. That is the reason we get the positive power output in part of oscillation and negative power from the part of its oscillation. Thank you very much for your kind attention and patience.
Thanks a lot, Professor Mahbub. And yeah, I was wondering why the baby bouncer, and then found that one. So any questions from the floor? Maybe we can have one question before moving to the next speaker. If not, thanks a lot, Professor Mahbub. And I think